Model 2, M/M/S, Infinity/FIFO model. This is a simple queue with Poisson arrival, exponential service time, multi-server, infinite capacity, and first-in first-out discipline. Characteristic of the queue. 1. The steady-state probabilities for n customers in the system Pn is equal to 1 by n factorial into lambda by mu whole power n into p0, if 0 less than or equal to n less than s 1 by s factorial s power n minus s into lambda by mu whole power n p0, if n greater than or equal to s, where p0 is equal to summation over n is equal to 0 to s1 1 by n factorial into lambda by mu whole power n plus 1 by s factorial into 1 minus lambda by mu s into lambda by mu whole power s whole inverse of minus 1. 2. Average number of customers in the queue or average queue length. E of NQ or LQ. LQ is equal to 1 by S into S factorial into lambda by mu whole power S plus 1 into 1 minus lambda by mu S whole power 2 into P0. 3. Average number of customers in the system. E of NS or LS is equal to LQ plus lambda by mu. That is, Ls is equal to 1 by s into s factorial into lambda by mu whole power s plus 1 into 1 minus lambda by mu s whole power 2 into p0 plus lambda by mu. 4. Average time a customer has to spend in the system. E of Ws equals Ls by lambda. That is, E of Ws equals 1 by mu plus 1 by mu into 1 by s into s factorial lambda by mu whole power s plus 1. Divided by 1 lambda by mu south whole square, 2p underscore 0 plus lambda by mu. 5. Average time a customer has to spend in the queue. E of Wq equals Lq by lambda. That is, E of Wq equals 1 by mu into 1 by s dot s factorial into lambda by mu whole power s divided by 1 lambda by mu south whole square into p0. 6. Probability that an arrival has to wait p of Ws 0 ton sticking out, n greater than s, equals lambda by mu whole power s into p0 divided by s factorial 1 minus lambda by mu s. 7. Probability that an arrival enters the service without waiting equals 1 lambda by mu whole power s into p0 divided by s factorial into 1 lambda by mu s. 8. Mean waiting time in the queue for those who actually wait. E of Wq given that Ws greater than 0 is equal to 1 by mu s lambda. 9. Probability that there will be someone waiting p of n greater than or equal to s plus 1 equals lambda by mu whole power s into p0 divided by s factorial into lambda by mu s divided by 1 lambda by mu s. 10. Average number of customers, in non-empty queues, who have to actually wait. LW equals E of NQ given that NQ greater than or equal to 1, equals lambda by mu s divided by 1 lambda by mu s. Problem. There are 3 typists in an office. Each typist can type an average of 6 letters per hour. If letters arrive for being typed at the rate 15 letters per hour, A. What fraction of the time all the typists will be busy? B. What is the average number of letters waiting to be typed? C. What is the average time a letter has to spend for waiting and for being typed? Solution. Given lambda equals 15 per hour, mu equals 6 per hour, s equals 3. A. Probability that all the typists are busy, tongue sticking out of n greater than or equal to 3. Equals lambda by mu whole power 3 into p0 divided by 3 factorial into 1 minus lambda by 3 mu equals 2 into 5 whole power 3 into p0 divided by 6 times 1 minus 2 into 5 divided by 3. We know that P0 is equal to summation over n is equal to 0 to S11 by n factorial into lambda by mu whole power n plus 1 by s factorial into 1 minus lambda by mu s into lambda by mu whole power s whole inverse of minus 1. P0 equals 1 plus 2.5 plus 1 by 2 into 2.5 whole square, plus 1 divided by 6 into 1 to 5 by 6 into 2.5 whole power 3 whole inverse equals 0.0449. Therefore, P of n greater than or equal to 3 is equal to 0.7016. Hence, the fraction of the time all the typists will be busy equals 0.7016. B. LQ is equal to 1 by s into s factorial into lambda by mu whole power s plus 1 into 1 minus lambda by mu s whole power 2 into p0 implies LQ equals 1 by 3 into 6 into 2 into 5 whole power 4 divided by 1 minus 2 into 5 by 3 whole square into 0.0449 is equal to 3.5078. C. E of W equals E of n by lambda equals by lambda into E of nq plus lambda by mu equals 1 by 15 into 3.5078 plus 2.5 is equal to 0.4005 hour or 24 minutes. Problem. A supermarket has 2 girls attending to sales at the counters. If the service time for each customer is exponential with mean 4 minutes, and if people arrive in Poisson fashion at the rate of 10 per hour, A. What is the probability that a customer has to wait for service? B. What is the expected percentage of idle time for each girl? C. If the customer has to wait in the queue, what is the expected length of his waiting time? Solution. Given s equals 2, lambda equals 1 by 6 per minute, mu equals 1 by 4 per minute. A. Probability that a customer has to wait for service equals P. N greater than equal to 2 is equal to 1 minus P0 minus P1. We know that P0 is equal to summation over n is equal to 0 to s minus 1 by n factorial into lambda by mu whole power n plus 1 by s factorial into 1 minus lambda by mu s into lambda by mu whole power s whole inverse of minus 1. P0 equals 1 plus 2 by 3 plus 2 by 3 whole square divided by 2 into 1 to 1 by 3 whole power minus 1 is equal to 1 by 2 P1 equals lambda by mu into P0 equals 2 by 3 into 1 by 2 is equal to 1 by 3 hence P of n greater than 2 is equal to 1 minus 1 by 2 minus 1 by 3 is equal to 1 by 6. B. Fraction of time when the girls are busy equals lambda by mu s equals 1 by 3. Therefore, fraction of time when the girls are idle equals 2 by 3. Therefore, expected percentage of idle time for each girl equals 2 by 3 into 100 is equal to 67. C. E of WQ, given that Ws greater than 0 is equal to 1 by mu s minus lambda equals 1 divided by 1 by 4 into 2 minus 1 by 6 is equal to 3 minute. Problem: a petrol pump station has 4 pumps. The service times follow the exponential distribution with a mean of 6 minutes, and cars arrive for service in a Poisson process at the rate of 30 cars per hour. A. What is the probability that an arrival would have to wait in line? B. Find the average waiting time, average time spent in the system, and the average number of cars in the system. C. For what percentage of time would a pump be idle on an average? Solution. Given S equals 4, lambda equals 30 per hour, mu equals 10 per hour. A. Probability that an arrival has to wait, tongue sticking out, of W greater than 0 equals lambda by mu whole power 4 into P0 divided by S factorial into 1 minus lambda by mu S equals 3 to the power of 4 P0 divided by 24 into 1 minus 3 by 4 is equal to 13.5 P0. We know that P0 is equal to summation over n is equal to 0 to s minus 1 by n factorial into lambda by mu whole power n plus 1 by s factorial into 1 minus lambda by mu s into lambda by mu whole power s whole inverse of minus 1. P0 equals 1 plus 3 plus 9 by 2 plus 27 by 6 plus 27 by 2 whole power minus 1 is equal to 0.0377. Therefore, P of W greater than 0 is equal to 13.5 into 0.0377 is equal to 0.5090. B. E of WQ equals 1 by mu into 1 by s dot s factorial into lambda by mu whole power s divided by 1 lambda by mu self whole square into P0. E of WQ equals 1 by 10 into 1 by 4 into 24 into 3 power 4 divided by 1 minus 3 by 4 whole square into 0.0377 is equal to 0.0509 hour or 3.05 minutes. E of Ws equals 1 by mu plus E of WQ equals 6 plus 3.05 equals 9.05 minutes. E of ns is equal to 1 by s into s factorial into lambda by mu whole power s plus 1 into 1 minus lambda by mu s whole power 2 into P0 plus lambda by mu is equal to 1 by 4 into 24 into 3 power 5 divided by 1 minus 3 by 4 whole square 2 into 0.0377 plus 3 is equal to 4.53 cars. C. The fraction of time when the pumps are busy equals lambda by mu s equals 3 by 4. Therefore, fraction of time when the pumps are idle equals 1 by 4. Therefore, the required percentage equals 1 by 4 into 100 is equal to 25.